Welcome back. This week, moving on to Chapter 5, talking about adaptations to aerobic and anaerobic training programs. Although, really, the focus of Chapter 5 is adaptations to anaerobic training programs, and then the focus of Chapter 6, the focus is aerobic training programs. But nonetheless, we press on talking about anaerobic training adaptations. So the idea here is if I engage in a sprint type training program or if I engage in a strength training program, how does the body adapt? That's kind of the overview of what we're going to talk about in this chapter. So obviously it does, your muscles get larger, you get stronger, you get more powerful, you get all these things. So we're going to get into the specifics of what happens in response to an anaerobic training program. In terms of anaerobic training, we touched on this a lot in Chapter 3 when we talked about bioenergetics. So if we say that training is anaerobic, what that means is that we are reproducing ATP without oxygen, right? And so we talked about the two broad ways of doing that. There's the phosphagen system, which includes ATP and phosphocreatine. And then there's also the glycolytic system, which is breaking down glucose, not in the presence of oxygen, so it's going through glycolysis, and then the end result of that is 2 ATPs and some pyruvate, right? And so those are the more powerful of the energy systems in terms of they can produce ATP relatively quickly. So for example, in the phosphagen system, you can reproduce 1 molecule of ATP in 1 step. Glycolytic system, you can reproduce or you can produce 2 molecules of ATP in 10 steps. As opposed to on the aerobic side, remember that when we add in oxygen, that's good because we can produce much more ATP that way when we add in oxygen because we can get rid of all the byproducts, we can get rid of all the hydrogens, we can get rid of all the carbon dioxide. But the downside is that system is much slower. It takes a lot longer to produce ATP that way. So it's described as not being as powerful. So anaerobic training, really what we're talking about here, again, is sprint type training or lifting weights, because for either of those things or those types of things, you're going to be using ATP so rapidly that you can't possibly deliver and use oxygen to the muscles and reproduce ATP aerobically at that high of a rate. So anaerobic training then is relatively high intensity training, so again, sprinting, lifting heavy things, where we can't possibly supply oxygen at that rate. So that includes, as you can see there, the anaerobic, the alactic system, so ATP, PCR, and then, as mentioned, the anaerobic or lactic system. So again, I'm trying to use their terminology here, and so then that's the glycolytic system. So particular modalities of anaerobic training include resistance training, so primarily lifting weights. Doesn't have to be actual weights, right? You can do body weight stuff, you can do strongman implements, any number of things like that. Those count as resistance training. Plyometric drills. So plyometrics essentially means that there is a rapid stretch, rapid contraction. In a sport context, we usually think of plyometric drills as jumping type drills. So that might be like running the agility ladder, which is what's pictured for you there. But that might also be things like box jumps. That could be medicine ball throws. That could be clap push-ups. Those kinds of things are plyometric type drills. And it also includes speed, agility, and interval training. So interval, some relatively intense work period followed by rest periods. If you're working on power, they're probably longer rest periods, or if you're working on strength, they're probably longer rest periods than the work period, but that type of training. So an important thing here, and we talked about this with EPOC, is that the aerobic system plays an important role in the recovery during rest or recovery periods. So what happens then is during sprinting or lifting weights, I'm running through ATP anaerobically, I'm using up my phosphocreatines, or I'm breaking them down to reproduce the ATP. I am breaking down glucose through glycolysis. And then during the rest period, so between sets or between sprints, I'm going to be breathing heavy relative to resting. And the reason that I'm breathing heavily is now I'm trying to use the aerobic system to try to remake those ATPs, or rephosphorylate those creatines, and then get rid of the lactate or lactic acid that was produced by using the glycolytic system. So we use the aerobic system to recover, we use the aerobic system to restore the phosphagen system, and then we use the aerobic system to get rid of the lactate that's produced if we exclusively use glycolysis anaerobically. So meaning if the results of glycolysis, pyruvate, don't go through the electron transport chain. So when somebody takes up a resistance training program, and like I said, this can include like speed and agility training, this can include plyometric stuff, but really here because this is strength and conditioning, we're primarily talking about resistance training, right? We're talking about lifting weights. So if somebody takes up a weight training program who is previously untrained, one of the first sets of adaptations that you're going to see are adaptations in the neural system. So we have adaptations in how the brain recruits motor units. We have adaptations in how that motor unit functions. We have adaptations in how the brain recruits particular muscles. And so those neural adaptations happen relatively quickly. So those happen over the course of the first several weeks. And then it takes a little while for muscles to grow. So muscular growth is hypertrophy, which we'll talk about in a minute, but that process takes a little while to make noticeable differences or make a noticeable difference in your performance. And so we typically don't see hypertrophy, so muscular growth, affect muscular strength and power appreciably until at least 4 weeks, probably more like 8 weeks after initiation of training. But you're going to see somebody get stronger after 4 weeks of training, even though they haven't really added any additional muscle mass. So how did they do that? And the answer is on this slide, neural adaptations. So these things here at the top of the slide, be familiar with those because there is at least one quiz question about those. So adaptations in terms of neural recruitment. So we get augmented neural drive via increased agonist muscle recruitment. So you recruit more of the appropriate muscles, right? So if we're doing something like elbow flexion, bending the arm, you get better, or the brain, the primary motor cortex most specifically, the primary motor cortex gets better at recruiting not only biceps brachii, your big elbow flexor, but also brachialis, also brachioradialis, and then some of the forearm musculature that also acts as agonists in elbow flexion. So you get better at recruiting the appropriate muscles. That's what the first bullet point is. Second one there, improved neuronal firing rates. So you get better at rate coding. Remember, rate coding describes the number of action potentials per second from a motor neuron. So how many times per second does that motor neuron depolarize, or how many action potentials per second does it send? Remember, with lower intensity contractions, maybe it only depolarizes 20, maybe 30 times a second. With really high intensity contractions, it's going to do that more like 80 times a second, right? And so in untrained individuals, they can't just ramp right up to 80. That does take some training. And then you also see some adaptations within the neuron as well, some changes in the sodium-potassium ATPase, so the sodium-potassium pumps can work a little faster, and that then facilitates that rapid firing rate that we see in response to training. Greater synchronization of the neural discharge. So we touched on this briefly before. So remember, there's a little bit of a difference between the way that we recruit muscles in strength and power activities and the way that we recruit muscles, or more specifically, motor units in endurance type activities. So when we recruit motor units for something powerful, let's say a vertical jump, we're going to try to recruit all of the motor units in my quad, all of the motor units in my hamstring and in my glute max, and we're going to recruit them all at the same time. Because if we can recruit them all at the same time, we're going to get a much more powerful action. As opposed to if we're engaging in, let's say, a cross-country race, what we're going to do then, because we're not running as fast as we can, we're probably running pretty fast, but we're not all out sprinting. And so because of that, we'll do what's called asynchronous recruitment, which means that you recruit basically a third of the motor units or a third of the muscle fibers at any given time on one stride, let's say in your quads, for example. And then on the next stride, you're going to recruit another third of the motor units. So that first third gets to rest during this second stride. And then on the third stride, you recruit the remaining portion of those muscle fibers or the remaining portion of motor units. And so now the first and second ones are still resting, and then we cycle back to the first. So the benefit there is, as I alluded to, you get some rest time for motor units between strides, and so that enables them to replenish their phosphagens, to get rid of any lactate, those kinds of things, and to get more oxygen into the muscle cells. So that improves their endurance, but that then decreases power output because we're not running as fast as we can. We're not recruiting them all at the same time. So with strength training, we get better at recruiting all of the motor units and recruiting all of them at the same time. So that's what that synchronization is. And then we get better at not tapping the brakes. That's the last bullet point there. So remember that your Golgi tendon organs, your GTOs, are proprioceptors inside the tendons of muscles, and that they have an inhibitory effect. So if the muscle is contracting too strongly, the Golgi tendon organs send an inhibitory signal back to the spinal cord, which shuts off the alpha motor neuron, causes it not to depolarize anymore. And then that causes reflexive muscle relaxation. And so again, the GTOs kind of act as a governor. Governor on like a U-Haul, if you've ever used a U-Haul while moving, they have governors on them, so you can't go above 60 miles an hour, whatever the governor is set at. If you try to go above 60, the engine kind of shuts down a little bit and then you slow back down. Same kind of idea with Golgi tendon organs. If you're trying to generate too much tension, they're going to shut the alpha motor neuron down, and so then you get reduced muscle contraction or reduced muscle activation and thus muscle contraction. And so what that does is it keeps you from damaging the muscle. And if you haven't lifted before, relatively low intensities are going to initiate this reflex, are going to basically tap the brakes on muscle contraction. But the more you get acclimated to heavier and heavier loads, essentially the brain gets better at interfering with that signal coming back to the spinal cord, and so we get inhibition or reduction in inhibition of the Golgi tendon organs. So as mentioned, these neural adaptations predominate or are the main mechanism of adaptation in the early part of training, especially if we're talking about somebody who's untrained, less so if somebody's been training for a long time and they just detrained. But with a new lifter, for the first 6 to 10 weeks, these make the biggest difference. And then after 10 weeks, and you'll see these numbers move around, but this is the one the NSCA uses, so we'll stick with this. After 10 weeks, hypertrophy, muscular growth, accounts for more of that improvement rather than neural adaptations. So in terms of neural adaptations, there are a couple different sets of them. The first is central adaptations. So central adaptations meaning central nervous system here. So we're going to see the primary motor cortex, which is that strip in the frontal lobe that initiates voluntary muscle contraction. Remember back in 201, I showed you the picture of the brain, the cross section that had the weird shaped people where they had really big faces and really big hands and feet and then relatively small arms and legs. So that was when we were discussing the primary motor cortex, if that's ringing any bells for you. And so what we do then is that part of the brain gets better at recruiting the appropriate motor units and gets better at recruiting them at the same time. And then the muscle cells themselves change, or the motor units, which includes the alpha motor neuron and then also the muscle fibers. So there's the definition of the motor unit, which you've heard before. Again, it's the functional unit of the neuromuscular system. So size principle, remember that we recruit motor units from small to large. So we recruit our type 1s first and then work our way up to the type 2As and then eventually the type 2Xs. And then we also rate code. So the alpha motor neuron fires more times per second, increases the frequency of discharge is another way of saying that. And so because of that, remember that if we are stimulating the muscle fiber really, really quickly, then it keeps depolarizing, so the inside of the cell stays positive. That causes calcium to stay out of the sarcoplasmic reticulum, allows for continued interaction of myosin and actin, and then that generates a stronger muscle contraction. So that's why the firing frequency or the firing rate of the alpha motor neuron matters, and we talked about this in some of the earlier chapters, so hopefully that's kind of old news at this point. And then selective recruitment. So again, this is the force velocity curve, which is kind of the inverted ramp. So if we're doing something that requires a really fast muscle contraction, a really explosive movement, remember that the type 2X fibers are so much faster than the other fibers that we actually kind of recruit things in a reverse order. We're trying to recruit the type 1s and the type 2As, but they're just too slow. So with really explosive activities, we selectively recruit the type 2X fibers in order to generate a really explosive movement. Now again, we're trying to activate the other two, but they just can't catch up yet. So there's our size principle. So we recruit the small motor units first, and then if we need high force production, then we're going to recruit the type 2Xs because those are the largest motor units and largest muscle fibers. We also, interestingly, get adaptations in the neuromuscular junction. So not only does the brain become more effective at recruiting the appropriate motor units and recruiting them at higher rates, if you will, in terms of rate coding, but we also see changes in the interaction between the alpha motor neuron and the muscle cell itself. And so that area where those two interact is the neuromuscular junction. And so you get an increase in total area. So the axon terminal, this thing, the yellow thing, gets a little bit bigger. And then the motor end plate here gets a little bit bigger as well. And so why that matters is if you've got more surface area on each of these things, you have more places to release acetylcholine from the motor neuron, and then you have more sites for acetylcholine receptors, those chemically gated channels, on the muscle cell. And so if we've got more surface area, we have more interaction between the two, and so we can get more sodium inside of the cell faster, we can cause it to depolarize faster. And causing the cell to depolarize more quickly, that's going to increase our power output and also increase our strength output. So greater end plate area, and then more acetylcholine receptors on the end plate. All right. We also, one of our really important reflexes gets more effective, and that's the myotatic reflex. I misspelled it on the slideshow that's up in Canvas. Sorry about that. I had it as the myotactic reflex, so I've corrected that for this. It's the myotatic reflex, and that's also known as the stretch reflex. And so remember that your muscle spindles, and that's what this diagram is, those are your muscle spindles. So remember that the muscle spindles are responsible for detecting muscle length, but also rate of change in that muscle length. And so they, unlike the Golgi tendon organs, and in fact just the opposite of the Golgi tendon organs, they cause an excitatory reflex when stimulated. So if the muscle is stretched too fast, they respond by causing the muscle to reflexively contract. And so the classic example there is that patellar tendon reflex. If somebody taps on a patient's patellar tendon, or if a doctor taps on a patient's patellar tendon, what happens there is that tapping on the tendon results in a rapid stretch of the quadriceps group. That rapid stretch is detected by the muscle spindles, and they basically say, uh-oh, the muscle is going to be overstretched, and it's going to be overstretched too quickly. That's going to tear the muscle. So to keep that from happening, we need to send an excitatory signal back to the spinal cord and cause the muscle to contract to protect itself. And so, again, if the muscle is stretched too quickly, stimulates the muscle spindles, they send an excitatory signal back to the spinal cord, then that activates the alpha motor neuron, and so then it is going to stimulate muscle contraction. And so why that matters then is that a muscle that's stretched really quickly is capable of contracting with more force and more power. And so we see that in counter movements. So for example, if you're going to do a vertical jump, you're not going to drop into a squat, stay there for a couple seconds, and then jump up. You're going to do a really rapid drop down quickly and jump right back up. And so unconsciously, you're actually trying to take advantage of this. You're trying to stretch your quads, stretch your hamstrings, stretch your glutes really quickly to stimulate that myotatic or that stretch reflex. And then in addition to that, the muscle itself has elastic properties, particularly as it's related to the connective tissue in the muscle, so the epiperi-endomysium. And so when that fascia is stretched really quickly, it wants to return back to its original shape as well. That's the elastic property. So there you get that combination of the elasticity of the muscle plus this myotatic reflex modulated by the muscle spindles. And so when you add those two things together, rapid stretch equals rapid contraction and stronger contraction. Both of those are additive with the contraction produced voluntarily. So with training, we get better at that, right? So that actually confers a stronger reflexive response. And you can see that that may increase by 50%. And so we get better at things like change of direction, which will be important for agility. And you see the myotatic reflex improve, particularly with plyometric type training. So again, that type of training is rapid stretch, rapid contraction. So things like box jumps or the agility ladder, all those are going to be, so to use the agility ladder, for example, let's say you're doing one-legged hops. That's going to be rapid stretch, rapid contraction of the calf musculature. And so if you do that regularly, that myotatic reflex actually gets a little more effective, and so we then increase subsequent power and force output. EMGs, so EMG is measuring electrical activity in muscle. There's a couple different ways to do it. There's surface EMGs, which are little stickers that you put on. They look just like if you've ever gone to the training room, the athletic training room, sorry, and had electrical stimulation done where they put those little stickers on you and then turn up the electrical current and the muscle contracts or you feel a tingling sensation. The pads look just like that, but rather than having an output, like distributing an electrical signal, they detect an electrical signal. So that's a surface EMG. And then intramuscular EMG, it's a fine wire. It's this little wire they actually jab into the muscle. Because one of the things about surface EMGs is that they're only good at detecting superficial muscles. Well, what happens if we're interested in the action of vastus intermedius, for example, because that's deep to rectus femoris. So we need to figure out a way to get to the electrical activity of that muscle, and so that's done through intramuscular EMGs. As you can imagine, not the most comfortable thing in the world to have a little, and it's pretty small, it's about the size of a hair, but to have a little wire in there while you're contracting a muscle. So other things as a result of resistance training or other adaptations as a result of resistance training, one of them is cross-education, which this one has always been fascinating to me, which is that if you lift weights on one side, like let's say you're a completely untrained person and we put you on a strength training program, a very selective research one, where we have you just do elbow flexion, so curls on your right side. And we have you come into the lab and do curls on your right side for 3 times a week for, 8 or 10 weeks. At the end of that, of course, your right side, your biceps on that side in particular, is going to be larger and stronger. But what you'll also see is an increase in strength on the left side. Even though you never did curls on that side, your left side still gets stronger. And so that is that cross-education. So basically, that is also probably an adaptation in that primary motor cortex where we get better at recruiting not only the side that we've trained, the right side, but we also get better at recruiting the analogous structure on the other side, so the biceps musculature on the left side. So you can see increases in strength on the contralateral on the other side, even if you don't train it. Bilateral deficit is that particularly in untrained individuals, the force of both limbs together is lower than the sum of forces produced unilaterally. What does that mean? That means if I had somebody do a one-legged squat on their right leg and a one-legged squat on their left leg and then add up how much they can squat, that number of right and left together is probably a higher number than if we just had them do a normal back squat. Now, that gets reduced with training, and so you get better at recruiting in similar patterns. And so you get better at two-legged movements with training, so that a reduction in the bilateral deficit. So bilateral means both sides, and so there's a deficit when you use both sides relative to using each side independently. And then reduced antagonist co-contraction. One of the things you're going to see when people are first learning a movement is they tend to contract all kinds of muscles inappropriately. And the same occurs with strength training. So for example, if you're doing elbow flexion, you might see excessive contraction of triceps. Now, triceps is always going to be active during a bicep curl, as counterintuitive as that seems, because tricep is going to be stabilizing the glenohumeral joint. But you'll see a reduced activation of tricep and maybe greater activation of posterior delt to stabilize the shoulder instead of tricep. And so then you get less antagonism from triceps, which then enables biceps to exert more force, right? And so you can lift more weight. How do the muscles adapt? The primary muscular adaptation is muscular hypertrophy, which means muscle growth. So anything that hypertrophies grows. So if you have, and it doesn't just apply to muscles, right? You can have liver hypertrophy. But hypertrophy means growth. So another term you'll see for that is increased cross-sectional area. So the cross-sectional area is the diameter of the muscle. And so a larger muscle has a larger diameter, and so it has increased cross-sectional area, which is abbreviated CSA. So anytime you see CSA, it's referring to cross-sectional area. And so what causes that increase in cross-sectional area is an increase in the number of myofibrils. So the myofibrils, remember, are inside of the muscle cell, and they're those little columns of actin and myosin. So you're going to have more myofibrils, and you have more myofibrils because you've generated more actin and more myosin. You've generated more of the contractile proteins. And so that's why a larger muscle is a stronger muscle, is because in response to that training, you've added more contractile filaments. And so if you've got more of the contractile filaments or the contractile proteins, then you have more actin-myosin cross bridges, then you can generate more muscle tension or more muscle force. And so that's why that matters. Muscle growth is stimulated in a few different ways, or actually really two different ways, broadly speaking. So it's stimulated by exercise-induced muscle damage caused by mechanical deformation. So when you cause the muscle to contract more strongly than it typically does, so if you're lifting heavier weights than you usually do, that's going to cause some damage to the muscle, and then you repair the muscle by, in part, adding more actin, more myosin, so then you end up with a stronger muscle, especially if you do that over the course of weeks and months. So as mentioned, it takes a little while before hypertrophy becomes an important factor in strength production. So it typically takes more than 16 workouts before hypertrophy becomes observable or apparent. And fast twitch fibers have a greater growth potential than slow twitch fibers. So slow twitch fibers can grow some in response to resistance training, but fast twitch fibers can grow more. They have a higher growth potential. So that's one of the things where genetics plays into this. To be an elite level bodybuilder like Phil Heath here, you have to have a combination of good genetics, good work ethic, and let's be honest, probably some drug use to be an elite level bodybuilder. And so if you have those right genetics of having, I didn't want to slander Phil Heath there, but realistically, most Mr. Olympias are probably using some anabolic agents. At any rate, he may not, I don't know. So there we go. I avoided slander. But anyway, to be somebody who is Mr. Olympia, to be somebody like Arnold Schwarzenegger, you have to have been gifted with a higher proportion of type 2 fibers, because those fibers then have greater growth potential. And if you have more fibers that have a greater capacity to grow, then that's going to help you get really big, like Phil Heath is there. All right. Other things. So the primary driver of muscle growth or of muscle hypertrophy is tension, right? So you have to cause the muscle to contract more strongly than it's used to contracting. And then in terms of damaging the muscle through tension, the most effective way to do that, the best initiator of muscle growth, is eccentric contractions. So you can see that's my second little bullet point there. So remember, that's when the muscle is contracting but lengthening. And so if we have that, that tends to cause more damage to the muscle cell, but also more damage to the connective tissue, which produces a larger inflammatory response, which then plays a really important role in initiating muscle growth. So the primary driver then of muscle growth is muscle tension. So if you lift heavy weights, that's going to damage the muscle and then cause you to rebuild. But there's a secondary driver of it, and that's metabolic stimuli. So if we do things that cause the pH of the muscle cell to drop, so if it gets really acidic, that can be a driver of muscle growth or muscle hypertrophy as well. So we can do that through high volumes and short rest. You can do sets of 10 and 12 with a 1-minute rest period, or 45 seconds, or sometimes you'll see 30-second rest periods, right? And so that's going to generate quite a bit of change in pH inside of the muscle, quite a bit of acidity, and then that appears to be a driver of muscle growth in addition to the amount of tension developed. So for example, from a practical standpoint, you see that many bodybuilders have relatively high volume programs where they'll do 5 sets of 12 of something, right? And so in doing that kind of volume, that creates that metabolic stimulus, and then that initiates or plays a role in muscle growth. Another way that we can do that as well is with occlusion training, and you're seeing more and more about this both in rehab research but also in strength and conditioning research. And so these two guys here have different occlusion bands on. So there's obviously one for the thighs, and then there's one for the arms. And so what you do with occlusion training is you lift relatively light weights. I think like 20% of your 1 rep max is fairly standard. And you have these bands. You can use blood pressure cuffs too. Basically, you inflate the blood pressure cuff, and then you do repeated, we'll use curls for example, because that guy's doing curls. You're going to do repeated elbow flexion motions with that blood pressure cuff on. And so with the cuff on, it reduces blood coming into the arm, but it keeps, and it also reduces venous return, reduces blood leaving the arm. And so then that induces higher metabolic stress in the working muscles, because we can't get oxygen to them, we can't get the lactate out, or we can't get the hydrogen out. And so because of that, induces greater acidity, and so that produces a greater metabolic stimulus. So that's another way to do that. Where you're seeing occlusion training in a rehab context, because I don't know, from my standpoint, like if you're a bodybuilder, just lift heavier weights and alter your sets, your reps, your rest intervals. I think that's much easier to do. Now, if you're, an elite level bodybuilder, sure, consider occlusion training. But there's a lot of setup that goes into it, so I don't know that it's worth your time. But from a rehab standpoint, it can be worth your time if you've got somebody who is coming back from an ACL repair and they're not ready yet to really load the joint. They can't lift really heavy weights, but we need to get muscle size back in order to get muscle strength back. And so rather than getting size back due to muscle tension, rather than really loading the muscle, we can just kind of do an end around and generate this metabolic stimulus to cause muscle growth. So I think it's really useful, or can be really useful in a rehab context, early in the rehab where heavy loading is contraindicated, where you shouldn't do it yet. So key point here, muscle growth, primary mechanism is hypertrophy. A possible yet unlikely mechanism is hyperplasia. And so hyperplasia, what you've got is that one muscle cell divides into two. That's what hyperplasia is. It's called longitudinal splitting. And I think that wording you'll see in the NSCA materials and also in the quiz bank. So longitudinal splitting is the splitting of one muscle fiber into two. There is some evidence that it happens in animals, but we can't do it in people because you have to take the whole muscle off and count the cells. And so, if you did that, they would not have that muscle anymore. So that'd be a problem. When they do it in animals, obviously they sacrifice the animal. So they do, a pre-post, or they do a training program, and then they do the untrained side compared to the trained side. But the animal gets sacrificed. So we don't do that with people. So there's not very good evidence for it in people, but we do know that bodybuilders and high-level strength athletes appear to have a higher number of muscle fibers than untrained people of the same age. And let's go with that. And so maybe the additional muscle fibers are the result of training, or maybe they're a really high-level bodybuilder or a really high-level weightlifter because they have more muscle fibers. So there's some chicken and egg there. So the thing that matters to you, hyperplasia, additional muscle cells, may happen in people, but if it does, it's probably not a big effector of muscle size nor of muscle strength. The main mechanism is muscle hypertrophy or muscle growth. Individual muscle cells increase in diameter, the whole muscle increases in size, and then you can exert more force. Do fiber types change? Not really. So to change in myosin ATPase, which is the enzyme on the myosin heads that breaks down ATP, so there is a little bit of a shift. So with training, like after you resistance train, your type 2X fibers will become more like the type 2As. They become kind of this intermediate type fiber. So basically what that means is that they'll add some more mitochondria, they'll add some more capillaries, they'll become slightly more aerobic, rather than being like purely anaerobic, almost no capillaries. So you get this shift kind of toward the middle. So they can go this way. And then with resistance training, the type 1s can become a little bit more like the type 2 fibers. So they can increase in size and they can become more anaerobic and that kind of stuff. But the myosin ATPase type is still the same. So they're still a type 1 fiber. They just resemble the type 2s a little bit more. So fiber type shifting happens some within a fiber. So your type 2s can move around a little bit. So again, they're going to trend toward the middle, so the 2Xs can become more like the 2As. The type 1s, you have to get into some really detailed literature before you start seeing multiple types of type 1s. But you can see there, so like the 1C can become a little bit more like the type 1. So there's some shifting within individual fiber types. Fast twitch can change their characteristics, but they're still fast twitch. Slow twitch can change their characteristics, but they're still slow twitch. So there doesn't appear to be any shifting. You can't make a fast twitch fiber into a slow twitch fiber or vice versa, as far as we know. In response to resistance training, you get some changes in the angle of pennation of a muscle as well. So remember, the angle of pennation describes the angle at which the muscle cells insert into the tendon. With strength training, because these little muscle cells get larger, it increases the angle of pennation. So resistance exercise increases the angle of pennation, pulls on the tendon a little bit, and as discussed in other classes, that then helps facilitate the increase in joint stability that we see after a resistance training program. Other adaptations that we see include alterations in calcium release from the sarcoplasmic reticulum. So you get better at releasing calcium more quickly and get better at taking it up more quickly, which then again facilitates interaction of actin and myosin or not. Increase in the cytoplasmic volume, particularly with high volume training. So kind of those bodybuilding protocols I was describing to you earlier of 5 sets of 12 with relatively short rest periods, those types of programs in particular appear to be effective at increasing cytoplasm or sarcoplasm volume. They also increase the sarcoplasmic reticulum density. So if you've got a better developed sarcoplasmic reticulum, you're able to store more calcium, able to dump more calcium, and get a faster interaction of actin and myosin. With resistance training, especially heavy training, you actually get a reduced mitochondrial content and a reduced capillary density, meaning that relative to the size of the fiber, there are fewer capillaries. But that's not because you lose capillaries or because you lose mitochondria. It's because the muscle cell has gotten larger itself, so its volume has increased, and we just haven't added mitochondria. We haven't added capillaries. And so because of that, you get a relative reduction in capillary density and in mitochondrial volume. We get a better buffering capacity, so we're better able to deal with a low pH, so acidity inside of the cell. And then we, of course, store more of the substrates, ATP, phosphocreatine, glycogen, and the enzymes to break them down, like the glycolytic enzymes that we talked about, or adenylate kinase, etc., in response to resistance training. Also, you get an increase in lean body mass. So what that means is when the muscles hypertrophy, you've added additional muscle mass, right? And so that's additional lean mass, lean meaning not fat. And with that additional muscle mass, that increases your resting metabolic rate, which is the number of calories you burn just sitting around, and so then that tends to produce a reduction in fat mass. So resistance training in particular, more than aerobic training, is really good at altering your body composition. So body composition is how much lean mass you have versus how much fat mass you have. So for example, you've probably done like bioelectrical impedance, where you hold on to little handles on a scale, or there's a machine that we have here, and they have in most kines programs, where you put in your age, your sex, your height, your weight, etc., and you hold this machine out with both hands, and there's little metal parts to it that you're holding, and it sends a little electrical current through you, and it'll say your body fat is 15% or something. And so that means that 15% of your total weight is fat, and then everything else is non-fat or lean mass, right? And so after a resistance training program, with the additional lean mass, with the additional muscle mass, again, we tend to see reductions in fat mass, so we see improved body composition. Obviously, after a resistance training program, you tend to see increased muscular strength, muscular endurance, and muscular power. Muscular endurance is the number of contractions you get before failure. And so even if you never do, sets of 50, sets of 100, that kind of stuff, if you just do heavy training, you'll see an improvement in muscular endurance. Bone also adapts. So bone adapts to compressive stresses. Also going to run two together there. Also torsional, so twisting, or traction stresses as well, but primarily to compressive stresses. So cortical and trabecular bone, I'm not going to rehash that, but just other than super briefly. So cortical bone's compact bone, it's out here on the outside of the bone. Trabecular bone, spongy bone, which is this stuff in here. Those are your trabeculae. Remember that the outer layer of the bone is covered, or the outer layer of the bone itself is the periosteum. And then the inner layer of the bone, we have another layer of cells, which is called the endosteum. And so under each of those, under the periosteum and under the endosteum, you have osteogenic cells. Osteogenic means generates bone. And so you have osteogenic cells where we can lay down new bone. And so in response to compressive stresses, primarily, or other types of stresses on the bone, that'll stimulate the osteoblasts, the immature bone cells, to lay down additional matrix. They're going to basically make a bunch of collagen. And then we will put our calcium crystals between those collagen strands, and then that'll help us to generate new bone. So the osteoblasts are going to lay down that matrix. So increased muscle strength or mass result in increased bone mineral density. Just means your bones are stronger. And so this bullet point here is the definition of bone mineral density, the quantity of mineral deposited in a given area of bone. So after a resistance training program, a long-term resistance training program, so longer than 6 months, you're going to see adaptations in the bone. Specifically, you're going to see increased bone mineral density. And so what happens then is those compressive loads, like the bone responds by essentially saying, like, because we're being crushed, we need to strengthen. We need to add some more mass here. Otherwise, we may see a stress fracture or something like that. So the bone responds to that loading by laying down additional mass. So the adaptations, as you can see there, take a long time, take more than 6 months, but we start the process of adaptation within the first few workouts. But some key things if you're going to train to increase bone strength, and where you might see this, of course, is in elderly populations. So somebody, or even somebody before they reach advanced age, if you're trying to prevent osteoporosis. So osteoporosis, porous bones, and that can result in fractures if they fall, or if their bones are porous enough, they can actually the bones can fail, like the neck of the femur or something that's a pretty common sight. So the neck of the femur can fail just due to normal loading because the bones themselves are so lacking in density, they're so porous. And so for somebody who is at risk of that, or somebody in the early stages of that, we might need to set up a training program to improve bone mineral density. So things to consider: specificity of loading. You have to load the area of interest. So if we're trying to prevent that femoral neck fracture, for example, we have to load the femoral neck. So we have to have them do things like body weight squats, for example. But we can also do it through other forms of weight-bearing exercise. So like in distance runners, you'll see increased bone mineral density essentially from the lumbar spine, so the low back, down. So the exercise, kind of key takeaways here. The exercise either has to be weight-bearing or has to be loaded. So weight-bearing meaning that you are like walking, running, jumping, those kinds of things. Or in terms of the upper body, because not many of us can walk on our hands, myself included, you have to load it. So you can do that by having them lift, dumbbells, barbells, any number of other resistance implements. And any of those resistance type things are going to compress the bone and result in bone remodeling, provided the intensity is high enough. So got to load the region of interest. So just because you're a runner doesn't mean you'll have high bone density in the upper body. You won't. Exercise selection. So to facilitate that specific specificity of loading, we ideally want to do total body exercises because we're going to get more bang for our buck if you do something like a deadlift rather than if you did, let's say, knee extensions, right? And then plyometrics seem to be the most effective. So because of the vibration forces associated with plyometrics, so if you have somebody do hops and jumps and those kinds of things, those are more effective at increasing bone mineral density faster than just having them do leg press or something of that nature. So the more vibration forces, the more we tend to stimulate bone growth. Now, of course, you got to be careful with that. Like plyometrics take a lot of strength, they do a lot of damage to the muscles, so you wouldn't just throw somebody out there on a plyometric program. There's a big lead up to it. But if you can train them enough to be ready to do plyometrics, then you can augment what you've already done with that plyometric training. Of course, progressive overload. So we have them lift heavier things, or let's stick with that. We have them lift heavier things than they're used to lifting. And then train variation. So if we want to maximize bone mineral density, you wouldn't just do squats and leg press all the time. You would work in maybe some unilateral stuff, so maybe like some one-legged squats, or have them hold a kettlebell on one side and then the other, that kind of a thing. And so by loading the bone a little bit differently, that will maximize mineral density. Your connective tissues adapt as well, so your tendons, your ligaments, and your fascia. And so the primary driver of the adaptation in those is the intensity of the exercise. So you can see the degree of adaptation is proportional to the intensity of the exercise. The more intense the exercise, so like the heavier you lift, the bigger the jumps, then the greater adaptation we tend to see in the connective tissue. And so, why that matters, of course, or why that happens, of course, is that as the muscle belly lays down additional actin and myosin, we can generate more tension in the muscle, but that doesn't matter unless the connection of the muscle to the bone also is able to withstand higher tensile loads. And so we add additional collagen to make sure that the connection to the bone can withstand those loads. So there's a question in the quiz bank that is related to all of these little bullet points. So changes in a tendon in response to loading include increases in collagen fibril diameter. So the fibrils, you can see a little fibril down here. They are kind of like a muscle cell. That's kind of the analog there. So you get more of them, which is down here, it's number 3. But not only do you get more of them, they get a larger diameter. So it's kind of like a combination between hypertrophy and hyperplasia. More cross-linking between the individual molecules inside of the microfibril, which is analogous to the myofibril. Increased density of the fibrils, so there's more fibrils packed into less space. There's less extracellular matrix, those kinds of things. And then increased tendon stiffness, in part because of increased cross-linking between the collagen molecules. And so all of that then adds up to an increased ability of the tendon to withstand tension forces. Cartilage also adapts to training. So one of the things about cartilage is that, because again, it's inside of the joint, so I'm thinking here of hyaline cartilage in particular, it's inside of the joints, it's avascular, so it doesn't have a direct blood supply, so it has to get, so the chondrocytes, the cartilage cells, they have to get their nutrients from the synovial fluid. And if we don't move, so if you're just, let's say you're immobilized, your joint's in a cast, for example, if you're not moving the joint, you're not moving the synovial fluid around, and so you're not nourishing the cartilage. And so what that does then is it can result in the death of some of those chondrocytes, and so then you get a thinning of the cartilage. Now, it's not really clear if adding resistance training and increasing the loading on the cartilage actually increases the thickness. We know that deloading causes a thinning, but we don't know if the opposite is true. Maybe, but we don't know that. Hormone responses, we talked about all this stuff in the last chapter, in chapter 4. There's nothing new here, so I'm not going to rehash it, but just be familiar with all of the ways to increase testosterone by manipulating training variables and to increase growth hormone. And the slide shows up with the relevant points. So there's the endocrine stuff. Cardiovascular stuff we haven't talked about. So in response to anaerobic exercise, so again, lifting weights for our purposes, so while you're lifting, the acute responses, increased heart rate, increased blood pressure, increased stroke volume, and increased cardiac output. Remember that Q is cardiac output. So because also remember that cardiac output is the product of heart rate, how many times the heart beats per minute, and stroke volume, which is how much blood is ejected with each beat. So as heart rate and stroke volume go up, then cardiac output goes up. So blood pressure increases in a more pronounced way during the concentric phase of the exercise. So when the muscles contract, they push down on blood vessels, both veins and arteries. And so on the arterial side, that narrows the arteries. And so it increases the resistance to blood flow, which is a way to think about that is that's an increase in diastolic pressure, so there's an increase in resistance to flow. So then there has to be an increase in systolic pressure to overcome that increased resistance. And so diastolic pressure goes up first, essentially, because of that increased resistance, and so then systolic pressure has to increase even more, and so you get an overall increase in blood pressure in response to resistance exercise during the exercise. Stroke volume and cardiac output increases in a more pronounced way during the eccentric phase. And that's because of that, during the eccentric phase, you get less resistance to flow, and so then that facilitates an increase in cardiac output. So chronic cardiovascular adaptations, how does the circulatory system change if you're somebody who is a power lifter, if you're somebody who's a weightlifter, or somebody who just is a regular weight trainer? How does your cardiovascular system adapt? That's what this is. So you may see a slight decrease in resting heart rate, probably not much. So if your resting heart rate's like 70, and then you do just like normal bodybuilding, powerlifting kind of training, at the end of, let's say, 12 weeks, your resting heart rate may be like 68, maybe. So it doesn't have a big effect on resting heart rate because it doesn't have a big effect on stroke volume. It has some effect on stroke volume, but it's not huge. Not like we see with endurance training. So you may see a slight decrease in resting blood pressure. Just anecdotally, it seems like the decrease in resting blood pressure is primarily a decrease in diastolic pressure. And then increased stroke volume. So the heart does get stronger in response to resistance exercise. But a key differentiator, and I'll show you, well, I'll talk about that in a minute. So you get an increase in stroke volume. May see a decrease in total cholesterol, may see a decrease in LDL, which is bad cholesterol, and potentially an increase in HDL, which is good cholesterol, the kind that scavenges up those plaques. And then little or no change in aerobic capacity. All right, so the adaptations in the heart are a little bit different between strength training and endurance training, and I think you've even seen this picture before. But essentially with strength training, because again, if you're thinking about something like a maximal deadlift, maximal squat, that lift itself takes several seconds, let's say maybe 3 seconds for the sake of argument. During those 3 seconds of concentric contraction, again, as the muscle shortens, its belly increases in diameter. That increase in diameter pushes down on the nearby arteries, increases resistance to flow, causes diastolic pressure to go up, which is that increased resistance to flow, causes the heart to have to pump harder to overcome that resistance. And so because the heart's having to pump harder for those few seconds, the heart's going to get stronger. But what we don't get is a big increase in venous return. We don't get a big increase in blood coming back to the heart. And so with strength training, you're going to end up getting a larger left ventricle, but because there's not a big increase in venous return, you're not going to really stretch out the heart, particularly the left ventricle, and so you're not going to see an increase in vessel size or chamber size. So with endurance training, because of those higher heart rates and because of those big venous returns, you're going to see, you're going to stretch out the left ventricle in particular a little bit more, and so that increased chamber size allows a really big increase in stroke volume. So in response to endurance training, you get a left ventricle that is larger in terms of the volume of blood that it can hold. It's thicker, so the wall is a little bit thicker, which means it can contract more strongly. And so you can eject more blood with each beat, so you have a higher stroke volume. In response to strength training, though, we just see increased thickness of the left ventricle with no real change in the diameter of the left ventricle, no change in chamber size. What about if I combine aerobic and anaerobic training? So what about if I do my cardio and I lift weights? Remember that the neuromuscular recruitment patterns are different between strength training and endurance training. Strength training, we see synchronous recruitment. Endurance training, we see asynchronous. And so if you are somebody who is a power type athlete, if you're a volleyball player, if you are a power lifter, weightlifter, if you're doing vertical jumps, those kinds of things, if you do a bunch of cardio stuff, that can decrease your power output because, again, it's going to teach the brain, hey, I need to recruit the motor units asynchronously, which then can cause some interference with that synchronous recruitment that we need for maximal power output if I'm doing something like an Olympic clean, right? So if you do endurance training, that can take away from your strength and power. Usually it doesn't matter unless you're trying to be a fairly high-level athlete. Just for general training, people, it doesn't matter a ton. In terms of order, if you do cardio second, so if you lift weights and then do your cardio stuff, that can interfere some with the intramuscular signaling of muscle growth, so that can hamper your gains, if you will, so your increases in muscle size, your hypertrophy. So just something to think about there. But if you are an endurance athlete, so if you're somebody like a cross-country runner, if you do really heavy strength training, then that's going to increase the thickness of the connective tissue around the muscle. It's going to increase your ability to engage in synchronous firing, so when you need it for the final sprint at the end, those kinds of things. So strength training tends to enhance endurance performance, but endurance training can hamper strength performance. That's the big change there. So no adverse effects of aerobic power when combined with resistance exercise, but some evidence that resistance exercise augments or improves in aerobic performance or endurance performance. Overtraining. So obviously, in order to cause the muscles to adapt, they have to lift more weight than they're accustomed to lifting, and so then that fosters adaptations. But of course, you can overdo it, and so that's overtraining. So overtraining, you see the definition there. So decreased performance, altered physiological and psychological signs and symptoms as a result of accumulation of excessive training stress. So typically with overtraining, it's something that happens over the course of several weeks to months. Too high volume, maybe too high frequency, too many days per week, and then maybe too high of an intensity for too long. Some combination thereof that leads to too high of a load causes what's known more colloquially as burnout, and that's overtraining. So we might do that intentionally, which is overreaching. And so we talked about this in the 345 class. You may have a period where you really ramp up volume and you really ramp up intensity with the intention of 2 to 3 weeks later really ramping it back down progressively as we go into a big competition, and that's known as tapering. So overreaching can facilitate some super compensation on the other side, but it kind of pushes you right to the edge of overtraining. So there's a fine line there. Overtraining, you can see the symptoms there. And actually, speaking of the symptoms, so this table 5.3 is important to know. There are multiple questions in the test bank for that. So be familiar with what non-functional overreaching is versus overtraining syndrome, and be familiar with the characteristics of it. So I would say have this up or handy during your quiz. So one of the things about overtraining syndrome is it kind of is this sensation that like you can see it's called burnout sometimes. You're just burned out, like you don't want to go train. And not only do you not want to be in the pool or you don't want to be in the gym, whatever your sport is, but you also see a decrease in performance. Like it feels harder and you still can't maintain the same pace. So we tend to see this in athletes who are, like you don't see this as much in team sport athletes, certainly you can, but oftentimes we see this in athletes who are like swimmers or track athletes. Swimmers in particular, because it's no impact, are notorious for doing really high volumes, and so they often really push that limit of that overreaching versus overtraining. And so you can see that overtraining may end an athletic career. There was an Olympian this summer, in the summer of 2021, those delayed games, who missed the games because she had kind of overtrained and gotten burned out, and then she just couldn't put it back together, and it sounded like she was going to have to retire. So it can be very, very serious and potentially end a career if you push it too far. So mistakes that can lead to that, so big increases in volume, intensity, training monotony, you just do the same thing all the time, and then you kind of develop a hatred for it. So too many competitions, because one of the things with competitions is as all of us know, you go harder in competition, right, than you do during practice. We always talk about making practices harder than competitions, but if you watch the number of people cramping up in early season football games, that's not true, right? That just doesn't happen. And so if we stack too many competitions close together, those repeated bouts of really high intensity performances then can lead to that overtraining. Keep in mind that athletes aren't just limited to the pool or the weight room or the gym or wherever they are. Other factors affect their stress levels, and stress is stress really. And so things like problems with their significant other, maybe some instability or food insecurity, any number of other things that can affect their feelings of burnout and maybe speed that up. So even though their training in and of itself isn't of sufficient intensity or volume to initiate overtraining, combined with some of the other stressors they have going on in their life outside of being an athlete, can then add up to produce overtraining. Detraining, use it or lose it. So if the body can adapt, the body can lose those adaptations. And so if you stop lifting, you stop sprinting, you're going to lose many of the adaptations that you've made. Not entirely. We'll do detraining first. So in terms of use it or lose it, if you stop lifting, you're going to maintain the strength for about 4 weeks. In terms of maximal strength, you'll see a reduction in muscular endurance, but you typically see a similar maximal strength for about 4 weeks, but sometimes it can taper off a little faster, maybe in as little as 2 weeks. So the initial change is you lose the neural adaptations, so there's some alterations in motor unit recruitment, some alterations in synchronicity, that kind of stuff. And then as we have a longer period of detraining, the muscles will reduce in size, so you'll get some muscular atrophy. But if they return to training So if they take 3 months off because life was hectic or they were traveling or whatever, you return back to that original point much more quickly than you got there the first time. So oftentimes that's referred to as muscle memory. So the brain relearns those neural adaptations really quickly. But the other thing is that we've talked before about how muscles respond in terms of the rebuilding process, that you damage a muscle cell, satellite cells migrate to the area, myotubes, all that. Those satellite cells that repair the muscle cell stay there. And so that muscle now has more nuclei, so it can build proteins faster. So when you train again, you're going to add that muscle mass back much more quickly because you have already incorporated those nuclei, so you can produce proteins faster. And so you're going to you're going to see a return back to that previous level of muscular hypertrophy and strength and power much more quickly than it took you to make those adaptations in the first place. And I put this one on there because I think it's a handy little chart. So it's table 5.2. And so here's all of the adaptations you see in response to resistance training. So increased muscular strength, increased muscular endurance, blah, 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 on down. So it's a handy little chart. And that is it. So that's the end of chapter 5. Next time we'll move on to chapter 6, which is adaptations to aerobic training. So we will see you then.